Yeah.
All right, so what I have here is a nice little triangle, okay? Now, if you think about it, this D3, right? It's moving at the speed of light, yes? So I can say the speed of light is equal to D3 divided by the time that I see it take Kyle's clock to get to the mirror. I'm gonna call it T prime. That's what it's usually called, even though it's not derivative or anything, right? Does that make sense?
What is T prime?
The time that I see Kyle's laser clock take to get from it being released to the mirror.
Is that a 1 or an 8?
Where? 1.
1.
Good?
Time is changing to the right time.
Yeah, I'm gonna do it. You guys understand? You guys understand?
Yes.
Yes? Okay. So I can replace D3 and say this is actually the speed of light times what I see Kyle's time at. Right? The time it takes, we'll call here to here a second in Kyle's time. Does that make sense? Okay. Here to here, this distance, right? This is what I perceive to be, so I'll just leave it as D1 for right now. So I would say that in my clock, then C equals D1 divided by my time. The time it takes my laser clock to be shot from here and hit the mirror. Agreed? Does that make sense? So I can replace D1 with the speed of light times my time. Agreed? You guys with me?
Yep.
Somebody hyperventilating over there?
Ariel. My calculator was not in degrees.
If it's just error.
Do you want my calculator? You can borrow
So,
Hey, just to say you lose your calculator.
sorry, I was actually worried for like half a second, and then I figured out who it was. So, now we basically need to figure out what D2 is.
A quick one.
Okay? Well, what is D2?
Square root of E3 squared.
No, we're gonna do that, huh? No, we can do better than that, right? So, think about it, right? This distance is this. So I can say the velocity of the spaceship that he's in, right, is equal to D2 divided by whatever time it took to go to here, right? Does that make sense? Right? This is actually the velocity of the spaceship. Agreed? So I can replace D2 with the velocity of the spaceship times time. Agreed?
Which time?
Fine. Because this, I witnessed it happen in that amount of time. I think it is. I'll know very soon if I'm wrong.
Okay.
Let's go. Good? So now if I want to relate the two, now I can use Pythagorean theorem. A squared plus B squared equals C squared. So, CT squared plus, actually I think I did do it wrong. Let's find out. So, plus VST squared is equal to CT prime squared. How I see his time.
Okay, so are all of this time?
Huh? No. So I'm beginning to think more and more this one is.
Okay, I think that was
I think that one is prime.
because
Because
yeah.
that's the time that I perceive.
See that one?
Yeah. Yeah, it is prime. Yep, that one's prime. Sorry about that. Because it's how far his rocket ship has gone and the time that I perceive his time is going one.
I'm sorry, could I ask why is time prime?
All right, so time prime, T prime, is the time that I witness that it takes his clock to go from here to here.
Okay.
Okay? T, just T, is the time it takes my clock to go from here to here. So this has to be the time that the distance the rocket ship went and the time it took his clock to go from here to here.
Okay.
Does that make sense?
Yes, sir.
Is okay? All right. So what we end up with is this, so we get c squared t squared plus v, I'm just gonna call it v, squared t prime squared equals c squared t prime squared. Right, that's just basically working the squares out. Good? I literally just squared all
Yeah,
this.
but could you just? Never mind.
Okay, I'm gonna subtract this over, so c squared t squared equals c squared t prime squared minus v squared t prime squared. Just subtracted this bit over. You guys follow me okay?
Yeah.
Algebra. I'm gonna pull a t prime out, so c squared t squared equals t prime squared times c squared minus v squared close. Guys good? Alright, now I'm going to divide c squared over. So t squared is equal to t prime squared. Yeah, I'm going to leave that out. So c squared minus v squared divided by c squared. That is not right. I want to basically get a ratio of the times. But I'm feeling, actually I'm nearly positive I've made an error somewhere.
Why is it even a
Pause
right
that.
triangle? Why is it even a triangle?
So t prime squared is equal to c squared t squared divided by c squared minus v squared. All right? Which is, it's just the same thing, except now I'm solving for t prime instead of t. All right? Okay, so now I'm going to, basically to make it look prettier, I'm going to pull a c squared out of the bottom bit. T prime squared is equal to c squared t squared divided by c squared times 1 minus v squared over c squared.
Why would you do that?
It makes it look prettier in the end. Alright, now the c squareds cancel.
Oh.
Alright, now I'm going to take a square root of both sides. So t prime is equal to t times 1 minus the square root of 1 minus v squared over c squared. And there's time dilation.
So time just increased?
Well, let's find out. Okay? Now,
Oh, no, no, you're right, you're right, you're right.
How did it become 1 over?
because I just pulled the t down, I mean, it was t squared, I square rooted both sides. All right, so what you end up with is this. So here's the idea. If your velocity is relatively small compared to the speed of light, right? And relatively small is pretty much anything that we're going to see on Earth, right? Then what does this basically become? 1, right? So, and 1 divided by 1 is 1, so t prime is equal to t. Which is why we don't experience time dilation in everyday life.
Is there just like really minuscule?
Yeah, it's very, very minuscule. Like when I take a step, when I'm doing this right now, your time and my time are different.
So like I'm getting older faster than you are?
Or the other way around.
Is that like carpet? It's like slowly get more.
I don't know. It's possible.
So if I run a lot in my lifetime,
Well, I mean, for cardiovascular health, yes. But they've actually proven this, that this works. And the way they've proven it is they took 2 atomic clocks, which are very, very, very accurate,
Oh, with
right?
the blackbirds around the
Yeah. And then they put one on the Blackbird, the SR-71, the fastest ship that we have, right? And they basically went as fast, I don't know if it went as fast as it could, but went really, really fast around the Earth. And they left one on the Earth. And when they got back, they were different by a very, very predictable margin.
And that was the margin.
And that was the margin.
Damn.
Right? So moving does change time relative to each other. Why?
But I mean, like, so like, if a person was to fly around the Blackbird for million times, right? They wouldn't like actually get older or younger faster.
Oh no, they totally wouldn't.
Like in terms of like age, like.
Time can't go back.
Wait, so like,
He's not younger than he was when he left. He's just not as old as you would have been.
Distracted.
Yeah.
so like, if you were to like fly away from Earth, like super close to the speed of light, and then fly back, it'd be like in the future.
Yeah.
Like a guardian.
Wait. But if you let that.
We wouldn't live forever.
The wear and tear on your body was.
Relative to
We
the
would
people
think
on
that
Earth.
it was still like that.
Right, that's actually one of my favorite science fiction concepts, right? So imagine that we make a spaceship that's really, really fast, right? So we make a spaceship that's really, really fast, okay, near the speed of light. And we send them to a, habitable planet 100 light years away, okay? So not 100 because then, let's say 30 light years away, which doesn't even make sense, but let's 30 light years away, okay? That means relative to them, they'll arrive at that planet 30 years later. Agreed? So let's say now time on Earth would have gone centuries during that time, right? Centuries. So this is one of my favorite ideas, is we send a group of brave astronauts 30 light years away from Earth, but 100 years after we send them, we discover wormholes, right? And we decide to colonize that. Yeah, so we decide to colonize that planet, right, using wormholes. We open up a wormhole and we're just like, let's go. Yes? By the time the astronauts get there, we've been on that planet for centuries. And then they would have just basically found out that their entire mission was a waste of time.
Literally a waste.
Like literally a waste of time. They had showed up like, all right, we can make, and this be like there'd be cities and like everything
They
going out.
would get like super praise.
And the thing, yeah, but everybody would know about them, right? They'd be like, oh, you're those dudes. Yeah,
The people we left in space.
yeah. See what had happened was, we're sorry, but we beat you.
But their investments would be worth a lot. if they
I mean, that's true.
stopped.
Humanity beat you here.
Humanity beat you here.
So
We've been
that'd
here
be
for a
crazy.
long time.
I'd
My
do-
bad.
Can't you also do like time travel, like to the future?
I mean, that's technically time travel, yeah. Like, you can go to the future, but you can't go to the past.
Heck.
Yet.
Like, what inspired the idea of time dilation? What inspired
Actually, Einstein was, and this actually leads me right up to our next point. Einstein was the best ever at thought experiments. He was amazing at them, right? He would sit, and he got in trouble in school a lot for it. He would sit and he would just close his eyes and he would do a thought experiment. He would basically do physics in his perfect ideal world, right? And one of them that he is most famous for is, so this is after they found out that the speed of light was a constant, or they hypothesized that the speed of light was a constant. And so Einstein was like, man, I wonder what it looks like though if I were to catch up with the beam of light. So he would do this thought experiment where he flies to the sun, right? And he sees this beam of light leave the sun and it's headed to Earth. And he just runs and tries to catch up with it. And he runs and he runs and he runs and he runs. And it seems like he's getting closer and closer to the front of the beam. And then just before he gets to the front of the beam and kind of gets to look at it, he'd wake up. Like it happened to him all, like for years, this would happen to him, right? And then he realized to himself, like mathematically, you can't catch up to the beam of light, right? It's impossible. Because, and this is how he figured out, is he's trying to catch up to the speed of light, and he moves fast, and he looks over at the light, and it's moving 388. So he goes faster, and it goes faster. And he goes faster and faster and faster, and it goes faster. And he really messed with his daydream because he's like, I can't catch up with it. So he's like, wait a minute, can that be accurate? So he did the math. He was one of the very first people that when Maxwell came up with the speed of light, he said, okay, what if this is true? What are the ramifications of it? Because everybody else is like, this is bull. That's not true. It's not how it works. And Einstein was like, no, maybe it is how it works. And here's the math behind it. Let's do it. And he figured all this stuff out.
It's like physics and
Wait, so if you try to
they make the running shoes.
Oh yeah.
And they
It
faster
takes
than light at the
infinite
beginning.
energy to go this
But they
fast.
tried. They almost caught up.
he says, dang, Ferb's light's just 2 times faster.
That's a really good question. Because light's a wave,
I didn't realize how scientific
Or is it?
Or is
that
it?
show
It's a particle.
which has
beats
mass.
sound.
Wait,
So
light
there-
has mass?
When it's a particle.
So light's like bipolar.
So, yes.
The schizophrenic.
Well, don't worry.
If light can do it.
Sure. Why not? So now, what we're going to do, so you guys see the problem, right? And if you think about it, this underlying statement kind of debunks everything we did in physics 1. Right? Because we derived, I mean, think about it. We derived everything from what? V equals D over T. Right? The very first question I asked you, day 1, physics 1, was, what is velocity? And you guys said, oh, it's a measurement of how far you've gone in a certain amount of time. That's what you guys told me, right? And I said yes, and we rolled with it, agreed? But here's the thing. We're making this assumption that time is time, right? We never actually thought that, you know, velocity is the distance that I agree to be a meter divided by the amount of seconds that I agree a second is, right? That was never a thing because Claire and I never disagreed on what a second was. Clovis and I never disagreed on what a meter was, right? A meter is a meter, a second is a second, but both of those are wrong, right? So everything we learned is, well, off. But everything that we observe on Earth, right? This V is nowhere near close to this, right? I forgot what this is called. It has a name. B squared over C squared. I think it's like, I don't know. It has a name. No. But think of it this way. What's the fastest thing you guys can think of on Earth?
Blackbird.
The blackbird. I mean, it's not. I mean, I think bullets go faster than the blackbird. I'm not sure though.
Depends on the bullet. Why don't we just make a
My
giant?
mom running at me when she sees me do the dishes.
All right. So how about this? Let's do this. Let's figure out what is the speed of a blackbird. So let me look it up. The SR-71 max
Dog
speed.
when I drop a piece of chocolate
Are
on the
you trying to, like,
ground.
pass a black-
In meters per second, please. He's trying to go higher.
Yeah, the altitude of a blackbird. I know, it's not just something about the
Miles per
blackbird.
hour
I
to
know.
meters per
First of
second.
all, we're gonna talk about
2,200 miles per hour.
2,200. Now, what is that in meters per second?
That's what I'm doing right now.
He sacrificed.
983.5.
983.5 meters per second. Okay, so do this. Let's figure this out. So do the math, okay? What is basically 1 minute? What is 1 minute blackbird time relative to us down here? Right? So we'll obviously think 1 minute is 1 minute. That's what T will be, right? What do we perceive them as having 1 minute? So 983.5 squared divided by 3e to the 8 squared. What?
Sorry. Are we plugging in C as
1
D1
minute,
over
60
T
seconds.
or speed?
What?
Light.
What?
Is C
Speed of light.
speed of light? Okay.
3 times 10 to the 8.
It should be slightly over 1.
You really did that in my head.
I don't need to do it in my head, it just makes sense.
So pretty much 1 minute.
Yeah. What'd you guys get?
Just 1 minute.
It's basically.
You get 1 minute. It's so incredibly small that even your calculator can't calculate it.
Calculator is just like.
And that's the fastest thing that we can think of on this planet. Right? So why don't we observe time dilation? Because we're nowhere close.
So if you get to the speed of light, then it becomes 1 over 0.
Exactly. So that's great. That's great though. Think about it. If we move the speed of light, okay? So let's say I'm on Earth and Adam moves the speed of light. what do I perceive his time being?
You don't.
Huh?
You don't. Or you can't.
Undefined.
His time
Isn't
stops.
Wait, how's it 1 over 3?
Because if he moves the speed of light at c squared over c squared, 1 minus 0, right?
1 minus 1.
Is 1. So, oh, wait.
No, 1 minus 1.
1 minus 1, sorry. I can do math with numbers. 1 minus 1, so 0, which makes this.
Wait, so he'd look like he's standing still?
He would look like he'd be like this,
But he's zooming across
but he's zooming across the screen.
Like flat.
Jesus.
So whenever he slows down, then would he start slowly?
He would start to move, yes.
Just be like, want to see how fast I can go, and then not move.
Here's a good thought experiment though. It's called Einstein's mirror. So let's say that this is a very interesting thing. So let's say Claire, who obviously is incredibly fast, is running near the speed of light. Let's say she's running, like she's outside, right? She is the Flash. She's running outside, the sun is behind her, right? And she's running near the speed of light, and she looks in the mirror. What does she see?
Light. Did you see the particles of the light?
She
What
wouldn't.
would she see?
Has it
I
not?
feel like she wouldn't see anything.
She would see herself behind herself.
Nothing?
Nothing, because it hasn't.
Wouldn't she would see herself, but like back in
She would see
time.
herself.
She would know,
Because
but
she
it's herself moving like
Yeah.
yeah, and come back to her.
She'd see a black.
And she's already up here.
Wouldn't she
A
see
black
like
man?
the past?
But yeah, but there's no lights here.
Oh, she never sees it. It never catches up.
Black.
It never catches up with her, right?
She would just see exactly what you would see if you put a mirror in front of you right now.
Lights.
Because relative to her, light is still moving at 3e to the 8.
Wait. But how's it supposed to surpass her, hit to the mirror, and come back? If she's
Because
moving at the
relative
same
to
speed.
her, it's moving 3e to the 8.
But it says that she's moving
But-
the same speed as.
So wait.
There's
Right.
nothing that-
It's always
So,
3
yeah,
idiots
but
relative.
wait a minute. But, so you're probably thinking to yourself, if I were to race the speed of light, right? If I was going to race a light beam, we both start at the sun. The light beam goes, I go, right? And if I'm going the speed of light, I should stay at the front end of that light, right?
Yeah.
No.
What?
Because relative to me, am I moving?
No.
No. Therefore, what is the light beam next to me doing?
Moving at 3.
3e to the 8.
But if you take your eyes and you move them behind you.
Nope.
But you're going the
3e to the
same
8.
speed and you.
What if you're blind?
Wait, but what if there's like a camera at the sun filming you?
You're faster if you close your eyes.
If
So
I'm
relative
right
to the
next
camera,
it
you go
and
the same
we're going
speed.
wouldn't I not look at its
Or are we?
Wait, do you run faster if you close your eyes and
Yes.
like you perceive the light?
Yes, try it.
Right now. Try it.
All right.
This is still going
If I'm
3 with 8, and you're just standing still.
right next
Yeah.
But she wouldn't see herself moving.
No. Well, yes, unless it's light.
That's why if you want to run fast, just don't move.
So you never
Light
realize
is
that you're running.
mathematically
What
proven
if you're running
first day. It's mathematically proven that light is always 3D regardless of how fast the observers move. It's the only constant that we can hold on to. Right? Which is why, right, I see this light beam moving at 3e to the 8, even though I'm just sitting there, right? But I see his going 3e to the 8, even though he's moving.
No.
Right?
Wait, this light.
It's basically just how electromagnetic waves happen, mathematics speaking. And like I said, they spent, Nima, I want to say, probably millions of dollars trying to prove that that's not the case, and they have failed every single time. What?
Does light move relative to time or relative to itself?
Yo, slow down.
What?
Because I'm thinking like, what if you froze time? It's like, does light
I
still
just
move?
want to freeze time.
I don't know. Hypothetically,
Take
if
a
you
picture.
could freeze
Take a
time,
picture.
That freezes time.
Yeah.
The picture.
Got you there, Mr.
Actually, technically, the way cameras work, each like row is seeing a different time.
Yes.
Okay,
Stop right-
wait, clarifying question. Okay.
clear.
So,
Fine.
okay, so let's just, you're running at the same speed as the light part.
Well,
Whatever.
you're running 3e to the 8 relative to something.
Okay, sure. Okay, so you're doing that, right? You're zooming across, and I'm standing right here. Okay? So, relative to me, is that light that's next to you moving at 6 to the 8?
No.
Or 3 to.
'Cause
Okay,
light's
but why?
always-
Because if it's relative to you, it's still moving.
No, that's the beautiful thing of it, right?
It doesn't make any sense because it's obvious.
So if I'm moving 3 to 8 and you watch me raise the speed of light, right, a beam of light, you would see me in the beam of light staying neck and neck, right?
Yeah.
That's what you would observe. But what I would observe is I'm not moving, that light just took off.
So the speed of that is actually 6 to the 8.
No,
No, it's still
because you would never see it at 60 to the 8. Nothing moves 60 to the 8. Nothing can go faster than 3 to the 8. It is the speed limit of the universe.
This would be a lot easier to see if you just write the equation for the speed of light right about now. 1 over square root of, what is it, epsilon naught at Planck's constant.
There though, that doesn't make any sense.
Okay, so moving on.
It's a bit much.
Yeah.
Oh,
So you're saying,
sweetheart, it's not gonna
so
click.
you're saying if I'm in space and I'm moving the speed of light,
Uh,
and there's a sun behind me,
yep,
but I'm moving 6 e to the 8 compared to the sun,
yep,
that the
Wait,
light
so it'll always
are
run.
going past me.
yes.
But people see you guys at the same, like.
Yeah. An observer outside at the sun
But wouldn't
would
the
see you moving.
observers
So
you
wait,
be more accurate? I'm so confused.
okay, accuracy is not a thing.
But you know what? It doesn't add up.
So if you're moving at like 6 e to the 8,
Welcome to
it's
research
relative
relativity.
to someone else, but relative to you, light's still moving faster.
What?
If you guys are neck and neck, how do you see something that's not there in front of you?
It is
gonna display you running this.
No. You're both
relative
running
to me. The light took
Since
off.
you're running at 6 e to the 8,
Okay, so
relative to you though, light's going.
let's talk about the thought experiment, right? Because if we're gonna start doing the math behind this, and actually, believe it or not, it makes more sense the more you just accept it. Trust me, that it's really weird. Oh, it's really weird, but the math starts working out beautifully. First of all,
I'm
like
really
I said,
submissive, so I'll accept
you
it.
can't go 3 to the 8 because it takes infinite energy for something with mass to go 3 to the 8.
Why does it take infinite energy?
I'll derive it later, right? But the idea is this. So you can't go. You can get really, really close, but you can't get there, right?
It's an asymptote.
Then it would be
So wait,
going.
but like, what if like, say like I was running a 3D EDA, right? And Liam was
Again,
running-
you can't, but
Yeah,
okay.
let's say I was, okay?
Wait,
No, he can't.
In a perfect physics world.
Okay.
Let's just say I was. Right? Let's say Liam was running next to me at 3D EDA, right?
Now,
Why doesn't Liam take on the property that light takes on and just like
well, because relative to you, Liam wouldn't be moving.
Okay, yes.
What?
Exactly.
Okay, but then why
Is Liam light?
Okay, but then why is
Liam's pretty heavy. I don't
That's
know.
true.
If okay, if relative to Kyle, Liam isn't moving, why is the ray of light relative
Because
to Kyle
light is an
still?
electromagnetic wave, right?
What is it? What is
Light
it doing? What if I
is
didn't
not
have
a thing, right? It's not a thing with mass, even though it is.
Half of
It
the time.
is a basically a fluctuation in the electromagnetic spectrum, right? So you can't expect something with mass to behave like something in the electromagnetic spectrum, except you can,
But
but
are we all weights?
Wait.
Yeah. Yeah. Wait. Hold on.
Okay.
We're all.
oh yeah, yeah. And now you're starting to see where parts of it don't gel,
Yeah.
but that's okay. We're gonna move on,
Okay, so you
or we'll stay here.
going back to what he said, we're both running at 3 to the 8, right?
Yeah.
So you said relative to him, I'm not moving.
Right.
Relative to myself, I'm not moving.
Right.
So I'm not moving, but I am. moving. Doesn't make
Relative
any
to who?
sense. Relative
When you
to everybody,
say
apparently.
when you say I'm moving 388, relative to who?
To myself.
No, you can't do that.
Okay, to someone else.
Fine, to Garrett.
But if we're running at the same speed,
Okay, so
Not moving?
relative to Garrett, you and him are going 388. He sees you going 388. Great. Relative to you, you're not moving. Garrett's going 388 the other way. And Kyle is not moving because you said you're going side by side.
Yes, that makes sense.
Okay.
That makes
I
sense.
feel
Light
okay.
does not make sense. That makes sense.
yeah, let's get a laser pointer.
Okay, so I want to get to a certain place with the thought experiment before we end today. So with the thought experiment, we need to basically set up a system for us to do calculations with things. You're fine. No, leave it. We need to set up a system so we can actually do measurements with things that are moving really, really fast. Okay? And the first problem is, how can we agree on a time? Right? How can we agree? Oh, the bag's in there. How can we agree on when something occurred? Right? So if we're really, really far away, okay, and we're trying to do measurements on something, like when something happened, right? How can we set up a system in our thought experiment so we can measure the amount of time it takes for something to go from point A to point B? Because we can't just sit there and use a stopwatch. That doesn't work, right? So how do we do it?
Always have an observer because they're
The idea is this. This is the, I'm just going to skip a bunch of crap. Also, while we're on the subject, Einstein also came up with this idea that gravity doesn't really exist.
Oh God. Wait,
Mom?
I can't deal with any mind shattering.
Try this then. What we need to do, it's a part of our setup. We need a free float frame in order for us to be able to do what we need to do. All right? And a free float frame pretty much works like this. If I put you in a dark box, okay, and I shot you out of a cannon straight up into the air, how would you be able to tell when you start coming back down?
You feel the acceleration.
Assuming no wind resistance, no friction, right?
You couldn't tell? You couldn't tell.
like because you're orbiting, you feel
What about on the way up?
If you don't feel anything, then there's like nothing to relate to, so you can't tell.
Yeah, you're always staying still.
Well, it depends if you're touching the bottom or if you're touching the top.
So you see when the cannon.
What? How would that happen?
It should be deep. I don't know. Well, okay. If you're there, if there's acceleration, you feel like that.
Okay. So you're in the black box, right? It shot up. What's the acceleration of the black box?
It's the acceleration's down here.
Of gravity, right? Yes? So what's the acceleration of you?
I'm accelerating
Gravity.
down.
Yes? Yeah?
Relative to me, nothing.
True. That's actually an accurate statement, right? So if the box is accelerating at the exact same rate that you're accelerating, right? Then how can you tell you're accelerating?
You're not accelerating. Zero.
Oh yeah, no, there's no wind resistance to light. But you can feel it.
How?
Like when you're on a roller coaster and then you go down and then you can feel without the friction and everything. You can feel it. You know.
He's right. You can.
You know. No, but that's, you know when you're moving up that fast.
Because a roller coaster is exactly what I'm referring to.
When you said that you shot me into the air while I was in a box, so excuse me for relating it.
Well, no, but think about it. The roller coaster isn't just letting you free fall. The roller coaster is pulling you down.
Yeah. But either way, I'm still accelerating in a direction, right?
Let's do the math.
Yeah, but the car is being pulled down. You're not being pulled down. You're not the car.
All right. So in order for you to basically for the box to apply a force on you, you need to have a normal force, right? Okay. So if you're in a box, so this be you, okay? You're shot up into the air, no wind resistance, no friction, no nothing, right? So this, zooming up is positive. Actually, I'll make down positive, so I can make, yeah, I'm gonna do that. Agreed? Yes? Now, we already agreed that what am I accelerating if I'm up in the box? G, right? So this is this. Yes? Right? So what's the normal force?
Oh, whoa.
Yeah, that makes sense.
Yeah.
Yeah. So therefore, how can you tell which way you're going? Now, let's say this is on the way up. Agreed? This is on the way up. What about at the tippity top?
It's still acting on.
It's the exact same thing. What about on the way down? Exact same thing. So how can you tell in any way, shape, or form
You
what
can't.
direction you're moving?
You can't.
I know this sounds stupid, but you know
You know why you feel that?
When because of
A change of acceleration.
that's what I'm saying though.
Change
Like when
of
we're
acceleration.
so you're saying since it's at a constant.
That just made sense.
Rolling acceleration, not weak. Rolling acceleration.
So, in order for you to actually be able to tell whether or not you're accelerating, right, you have to have some reference frame outside of what you're doing. So, if we take Nima back out in space, right, can we even tell if Nima is accelerating? No. As long as the acceleration is constant, we actually can't even tell if Nima is accelerating. Because she'll be accelerating relative to nothing. Make sense? And that's the idea behind a free float frame. We're done. I'm not done.
Because he's about to run out of battery.
Well, sucks for the people who missed my lecture.
Well, I mean,